Plastics encompass a diverse group of synthetic and partly synthetic materials predominantly made of polymers, which are long chains of repeating molecular units. Their most notable trait, malleability, permits them to be shaped into countless objects through molding or pressing, a flexibility paired with qualities like low mass, resilience, and resistance to many chemicals. These features, along with relatively low production costs, have encouraged their adoption across the globe, from packaging and construction to medicine and vehicles. While most plastics originate from petroleum and natural gas, a modest portion now comes from renewable sources such as polylactic acid. From 1950 to 2017, production climbed to nearly 9.2 billion metric tons, with more than half produced since 2004, and recent annual output already surpassing 400 million metric tons. Projections suggest the world could see production top 1.3 billion tons by 2060 if current demand persists. Packaging stands as the primary use, accounting for nearly 40% of plastics, while building materials like polyvinyl chloride pipes rank second. They also appear in transportation, furniture, and household goods, with distribution patterns varying among countries. For example, in India, packaging forms an even larger percentage of consumption. Since the invention of Bakelite in 1907, credited to Leo Baekeland, chemists such as Hermann Staudinger and Hermann Mark have revolutionized polymer sciences, broadening plastics' reach. The term plastic traces its roots to ancient Greek, conveying the idea of something that can be molded or formed apt, given plastic's adaptiveness. Structurally, most plastics consist of carbon-based polymer chains, sometimes including oxygen, nitrogen, or sulfur atoms, from which side groups project, determining the plastic's specific traits. Classification hinges on chemical structure, synthesis method, or physical attributes like strength, density, or thermal behavior. When considering thermal properties, plastics are typically grouped as either thermoplastics materials that soften and can be reshaped with heat, or thermosets, which harden irreversibly. Commodity plastics such as polyethylene, polypropylene, polystyrene, and PVC dominate mass production, filling roles in everyday items ranging from food packaging to simple utensils. These represent about 4/5 of output, but are often linked to the mounting problem of plastic waste in natural environments, as a mere fraction is recycled or incinerated, while most ends up as landfill or pollution, notably in marine ecosystems. Microplastics, fragments resulting from degradation, spread widely and raise health and ecological concerns. Engineering plastics, valued for enhanced strength or endurance, find roles in automotive components, electronics casings, and specialized machinery. High-performance plastics, distinguished by their sturdiness, resistance to heat and chemicals, and specialized uses, appear in fields like medical devices, aerospace, and even body armor. Some plastics, termed amorphous, lack ordered molecular arrangements, while crystalline types show regular patterns, a quality affecting their melting and glass transition temperatures. Some plastics conduct electricity, especially newer blends like poly-3,4-ethylenedioxythiophene, polystyrene sulfonate, although not at the levels typical of metals. Others are designed to break down under natural conditions or derive from plants, known as bioplastics, with polylactic acids leading in commercial visibility. Despite their convenience and utility, plastics pose serious problems because they persist in the environment, resist natural decay, and are rarely reused or recycled, contributing to pollution in land and sea. As global production expands and shifts toward more sustainable feedstocks, the evolution of plastics continues to influence daily life and planetary health. The plastic sector spans worldwide activities from raw material production to the transformation and sale of plastic goods. Key petrochemical inputs are mostly sourced from the Middle East and Russia, yet manufacturing clusters are concentrated in both eastern and western regions of the world. The sector is vast, with thousands of firms operating in several spheres such as material production, compounding, and product fabrication. Since plastics emerged as a significant commercial material in the mid-20th century, production volumes have seen immense growth, especially after 2004. Around 9.2 billion metric tons were produced between 1950 and 2017, with annual global output reaching roughly 400 million metric tons in 2021. Forecasts suggest yearly production could more than double by 2050 if current demand persists. The increased availability of cheap raw materials and significant investments fueled rapid industry expansion in Asia, notably China, which by 2020 accounted for just under a third of global plastic resin production. Europe and North America historically led this market, though Asia's footprint has grown markedly in recent years. Now over half of global manufacturing happens in East Asia, while around 1/5 is in North America. Regional output is shaped by market needs, fossil fuel prices, and local investment into petrochemical infrastructure. For instance, the United States attracted considerable development support due to reduced feedstock costs, and the European Union hosts millions of workers across this sector, generating several €100 billion in annual revenue. China alone registered well over 15,000 producers by 2016, with revenues surpassing $366 billion. Most plastics are derived petrochemically and created by polymerizing simple monomer units in facilities reminiscent of refineries, but with specialized equipment for polymer production. The sheer size of these plants means economies of scale are obtainable, though the market does not fall under the control of a few giants. Around 100 firms collectively represent 90% of worldwide output, with a mix of both privately held and government-run organizations. Thermoplastics, which can be repeatedly melted and reshaped, dominate the market. Key varieties such as polyethylene, polypropylene, polyvinyl chloride, polystyrene, and polyester-based fibers form the core group, accounting for the vast majority of production. Before reaching the final consumer form, plastics generally undergo compounding, where base resins are blended with chemicals that modify their ability to resist degradation, add color, or otherwise change their properties. Some products use high concentrations of these additives to create a material known as masterbatch, which can later be blended with more basic resins to achieve a desired outcome. This method is especially common when producing colored plastics. Larger companies may handle this internal blending, but specialist third-party compounders serve many others, using equipment such as extruders that can achieve the necessary mix at elevated temperatures. Once compounded, plastic resins are shaped into products by processors known as converters. Various fabrication methods are common. Injection molding forces liquid plastic into a mold to produce solid objects. Blow molding expands warm plastic into hollow forms, useful for bottles. Rotational and casting techniques create hollow or complex components, and film blowing creates flexible sheets for packaging. 3D printing has also become a recognized approach for crafting objects directly from digital models. Thermosetting resins begin as liquids and must be hardened or cured during manufacturing, though many of the machines used resemble those for other plastic types. Packaging represents the largest application, with items such as bags, films, containers, and bottles, mostly composed of low or high-density polyethylene and PET plastic, accounting for more than a third of all plastic use. Many of these are designed for disposable, short-term use, often lasting less than a day. Other fields, including construction, textiles, vehicles, and consumer electronics or goods, also claim significant shares. Items in these groups tend to have longer service lives, ranging from several years to multiple decades depending on their function and environment. Patterns of plastic consumption vary globally based on geography and population. North America and Western Europe have the highest per capita usage, while China, owing to its population, ranks nearly equal to North America in terms of total volume consumed, despite lower individual usage rates. Beyond packaging, plastics can be found in construction pipes and window frames, household and personal items, vehicle parts, electronics, textiles, and even optical lenses. Manufacturers blend various chemicals into plastics to alter their function or enhance their look, making plastics highly versatile and widely adopted. Each product generally contains multiple additives, often not disclosed to consumers. In the European Union, hundreds of additives are used in high volumes, while a global survey identified thousands. Every form of plastic contains at least some stabilizers to allow molding without deterioration. For items like polyvinyl chloride pipes, additives can make up a majority of the material. Plastics rarely appear on the market as pure resins. Most contain a combination of additives, which may attach loosely or remain chemically distinct. Over time, these additives can seep back out during use, disposal, or in landfills, sometimes degrading into substances that are either less or more toxic. When plastics break down into tiny fragments, these chemicals can be carried far from their point of origin and persist in ecological systems, sometimes accumulating in living creatures. Regulatory bodies have found dozens of chemicals in plastic associated with significant risks to health and the environment. Recycling poses unique challenges because the variety of additives found in plastic waste complicates the production of new materials with consistent characteristics. Sorting plastic by type and color is necessary to avoid undesirable mixtures like dull or brownish recycled products. Lack of clear labeling about which chemicals are present makes monitoring and regulation complicated. For instance, certain flame retardants or past use of metals like lead, cadmium, or mercury are now recognized as dangerous and are subject to regulation in many regions. Restrictions differ globally, and even where banned, these substances sometimes appear in packaging or other consumer items. When plastics are burned carelessly, especially in less developed regions, incomplete combustion releases pollutants like dioxins, which can linger in the body and accumulate up the food chain. International treaties aim to protect people and wildlife from such hazards. Some compounds, such as bisphenol A, BPA, are banned in specific applications like baby bottles, in some countries but remain in use elsewhere. The health consequences of plastic additives and their breakdown products are complex. Many items require plasticizers to remain flexible, but compounds like phthalates can migrate out and are restricted in toys or food contact materials in some regions. Some substances leaking from food containers may disrupt hormones or have carcinogenic properties. Additionally, manufacturing off-gases or residues such as vinyl chloride are associated with cancer risk. New fields of concern continue to emerge, as in the discovery of plasticosis, a disease in birds caused by ingesting plastic fragments, which leads to scarring within their digestive tracts and can disrupt feeding and survival. The diverse range of additives each serve a purpose. Plasticizers increase pliability, flame retardants slow burning, heat stabilizers prevent breakdown under heat, fillers bulk up materials or adjust characteristics, impact modifiers boost toughness, and other chemicals tweak color, reduce static, or aid processing. Each class of additive makes up a measurable share of global usage, with plasticizers and fillers constituting the largest portions. Of growing concern is the environmental persistence of plastics and their fragments. Microplastics, defined as synthetic solid particles less than 5 millimeters in size, enter the environment from sources such as textiles, packaging, or the breakdown of larger items. Both primary and secondary microplastics remain widespread, especially in marine habitats, but also accumulate in soils and the air. Plastics and their byproducts, due to their slow breakdown, are often ingested by wildlife, causing harm at multiple biological levels. Some microorganisms, like certain fungi or gut bacteria of cockroaches, have demonstrated the ability to break down plastics, but such processes are not widespread in nature. Production and recycling of plastic fundamentally impact the environment. Globally, only a small fraction of plastic waste is recycled. Most recycling involves remelting and reshaping, which can further degrade plastic quality and sometimes release additional microplastics. Chemical recycling or burning of waste plastics is practiced, though the latter can emit harmful or greenhouse gases. Comparisons show that manufacturing plastics requires more energy than many common materials, though less than electronics manufacture. There is increasing attention worldwide to the need not just to recycle, but to reduce overall production and consumption of plastics due to their share of global emissions. Some studies suggest that, in certain cases, alternatives to plastic may have even higher environmental costs, especially when factoring in greenhouse gas releases. Policy efforts are underway to develop agreements aimed at addressing plastic pollution throughout its life cycle. Historically, plastics evolved from natural materials like rubber or shellac to chemically modified forms using milk proteins or cellulose, and ultimately to entirely synthetic forms such as bakelite or polyvinyl chloride. Mass production took off after the Second World War, with continual development and the introduction of polymers for everything from bottles to textiles and electronics, and eventual growth in recycling and efforts to mitigate environmental damage. As plastics move globally through production, use, and waste, their chemical complexity, durability, and stubborn presence in ecosystems continue to shape environmental and policy discussions.